Check the mic and make sure it sound right, boys.
Hey everyone, and thanks for tuning in again. In today's video, we'll be looking at how to compute correlations in R, as well as run some regression analyses. The first example for regression that we'll be looking at is a simple linear regression, which is a regression analysis with one predictor. The second example is a multiple regression analysis, and for our example, we'll be looking at two predictors. After running these regression analyses, I'll also be going over how to interpret the results, and I'll be providing some example write-ups. So let's go ahead and open up RStudio, and we'll get started on the lab. Alright, so now that we have RStudio open, I have this template that I've created. Essentially, it's just comments that are helping to organize my syntax file and the syntax that we're about to type out. If you'd like this file, it's called week4_template R, and I've uploaded it online. In addition to the template, I've also uploaded this new data set called regdata2. So we're going to be switching over to this new data set called regdata2. And it's a tab delimited file, so the extension is .dat. So where we'll start is reading in our data set. So we're going to call our data set regdata2. We're going to use the read.table function to read in the tab delimited file. And then remember that within quotes, you'll want to list the path name. So as with the other data sets, my own data set is located in the C drive in the datasets folder. And it's called regdata2.dat. And then the next argument, which is separated with this comma here, is header, and I'm going to say true because the first row of my data set are the variable names, and then another comma, and then here we have sep for separator is equal to a tab. So all of my observations in my data set are separated with a tab, and to specify that, we just type backward /t, and that goes in quotes. Alright, so I'm going to go ahead and read this data set in. And to run these lines of code, again, as I mentioned before, I'm just pressing Control and Enter on my keyboard. And that'll run the syntax line by line. So I'll go ahead and run that, and here we see that regdata2 was read in, 100 observations with 6 variables. So I'll click on it just so that we could take a look. And similar to the data set before, we have our y variable, and then we have 5 predictors, x1 through x5. And we should have 150 observations. So as I scroll down, perfect, 150 observations. So that looks good. Okay, so we'll start with correlations, and what I'll show first is how to compute a correlation between two variables. So let's say I want to look at the correlation between x1 and y. So I'll start by typing core. This is the core function, and we want to look at the correlation between x1 and y. Now, if you remember from last time, the way that we're specifying our variables is we have to type the data set first, followed by a $, and then after the $, the variable name. So essentially, x1 is a variable that's coming from regdata2, and y is coming from regdata2 as well. So I want to get the correlation of x1 and y, which are both in the regdata2 dataset. Once I have that, I could just go ahead and run this line here. And here in the console, we get our computed correlation, which is 0.24. All right, simple enough. So let's move on to computing a correlation matrix for all of the variables in our data set. So for y, and then x1 through x5. We're going to use the same core function, but instead of typing in our two variables, we're going to type in the data set. And if we run this line here, you can see we get a correlation matrix for the whole data set. So we have y, x1 through x5, excuse me, for the columns, and as well as for the rows. So On the diagonal, we get 1s because each variable correlated with itself is a perfect correlation of 1. And then we get our correlations here. So the way you read it is x1 with y is 0.24, and we saw that earlier. x2 with y is 0.30. x3 with y is 0.29, and then just picking another random spot, x3 and x4 is 0.046. Okay, so that's a simpler way to get more correlations quicker, or if you just want to see how all of your variables are related to each other, using the core function on the data set instead of just the two variables gives you that correlation matrix. Okay. I'm going to show here that if we, actually, let me just copy and paste this. And if we wrap this core function with regdata2, if we wrap it with the round function, here is a comma, and I want 2 decimal places. So if we just wrap the core function with the round function and we run this, I get a correlation matrix that's a little bit more manageable. So this is a lot easier to read here than the correlation matrix with a bunch of decimals that we don't need. Okay. Now let's say you want significance tests with the correlations. We don't get that using the core function, so we'll move on to a different function. So the package I'm going to use here is hmisc. So capital H, lowercase misc. If you don't have this package already, you can go ahead and download it using the install.packages function. So I'm going to go ahead and run this line to load the package. And now that it's loaded, I'm going to create this object called regdata2 matrix. And what I'm doing here is to use the rcore function, which is in the hmisc package, which will give us significance tests with our correlations. I need to change the format of our data set here to a matrix, because right now it's a data frame. So this thing called regdata2_matrix is going to be our regdata2 data set, but instead it's as a matrix. And that's why I'm using the as.matrix function. Once I run that, I can use the rcore function on regdata2_matrix. And to specify the type of correlation, we use type equals, and we want Pearson correlations. So I'll go ahead and run this line first, creating the matrix instead of the data frame, and then I'll go ahead and run the rcore package next. So as you can see here, we have our correlation matrix first, and then we have the corresponding p-values down here. So if we're looking at the correlation between x1 and y, which is right here, 0.24, the corresponding p-value can be found here, x1 and y, and the p-value is 0.003. So that's less than 0.05, so that's significant. Alternatively, if we look at the correlation between x1 and x2, which is 0.09, if we look for the p-value x1 and x2, it's 0.29, which is greater than 0.05, so that's not statistically significant. All right. So that's it for correlations. And so moving on, we're going to run our first simple linear regression example. Now, simple linear regression is just a regression with one predictor. And so to start this, I'm going to create an object called model1. And to estimate our linear regression model, I'm going to use the lm function for linear model. And I want to predict y from x1. Now, I'm not doing the dataset $ format here because I'm going to tell the lm function that my dataset is equal to regdata2. So here, for this formula, within the lm function, I could just use the variable names, and then in the next argument, I use the data statement here, data equals, to specify that these variables are coming from the regdata2 dataset. Okay, that will estimate our regression model, and then to get the output, we have to use the summary function on the object with our model. So model 1 is the object that contains our regression model. So I'll go ahead and run this first. That'll estimate the model, and then I will request a summary of model 1. Alright, so here's our output. We have our formula here, y predicted from x1. This is essentially the syntax that we just wrote. And so here is the stuff that we're interested in. So we have our intercept, which is 41.24. That's when x is equal to 0. And obviously that is much larger than 0, so this is significant. It's no surprise that this is significant here. But what we're really interested in is the slope. So we have our regression coefficient here, which is 0.7966. We have the standard error, the t-value, and then the significance of that t-value, which is 0.00295. So that's less than 0.05. So our regression coefficient is statistically significant, and so we can say that it significantly predicts y. And then down here, we have our r squared, which is about 0.05815. So we can say that about 6% of the variation or the variance in y is explained by x1. We have our adjusted r squared here. Essentially what adjusted r squared is it penalizes you for each added predictor. So if you add a predictor to your model that doesn't carry its own weight or doesn't provide a substantial amount of prediction, the difference between multiple r squared and adjusted r squared the difference will get bigger and bigger. So the bigger the difference between these two numbers here, it's stating that there's predictors in your model that aren't contributing a significant amount of prediction. And then finally, we have our F statistic here, which is associated with the ANOVA that we run for our regression. So we have an F statistic of 9.138 on 1 and 148 degrees of freedom. And then we have our associated p-value, which, since we only have one predictor, matches the p-value for the test of the coefficient exactly. So these are both the same exact value and both less than 0.05, so they're both significant. Okay. So now what I'll show you is how to run the same model, but to get the standardized coefficients. So I'm going to go ahead and just copy and paste this here and make some adjustments to the code. Alright, so I'm going to create a new object, and I'm going to call it model1_scale. And all you have to do to get the standardized coefficients is wrap the variables in the scale function. And what the scale function does is it standardizes the variables. So just make sure that the summary here is for model1 scale and not model 1. So if I run this and then run the summary, I get my standardized estimates here. So we're just focusing on the estimates. Everything else should be, or everything else that we care about should be the same. So here we have 1.403 e to the negative 16. So that means that we move this decimal point here 16 places to the left. So that's a really, really small number. It's effectively 0. And then for our coefficient here, we move our decimal point to the left 1 place. So essentially the coefficient is 0.2411. Significance value is the same. R squared and adjusted R squared are the same. F statistic is the same. Degrees of freedom the same. P-value the same. So when we run our model using the scale function around our variables, all that we're interested in are the standardized coefficients, which for the intercept is here, and for the slope is here. Okay. Before we move on to the multiple regression example, I'll go ahead and show the example interpretation for the simple linear regression, or the one predictor regression. So a simple linear regression was conducted to test the linear relationship between y and x. The results of the analysis suggest that y is significantly predicted by x. And so here I present the f value. This is called the statistical sentence. And so what I have here is f with 1 and 48 degrees of freedom is equal to 9.14, and p is less than 0.05. And so going back to our R studio, all that information is coming from here with the associated p-value here. Okay. And then approximately 6% of the variance, this is our R squared, and y is explained by x1. And then here I move on to the interpretation for the regression coefficient. So for every 1 unit increase in x1, y is expected to increase by 0.80 units, and that's with rounding. And then another statistical sentence here. This is redundant since we only have one predictor. This is redundant with the f-test, but I report it here just for completeness. So t, and this is on 148 degrees of freedom. And the easy way for me to remember what the degrees of freedom should be for the t-test is it's always the error or the residual degrees of freedom. So if we go back to our RStudio, you could see here in the output, let's see. Oh, here. So we have the 1 and 148 degrees of freedom, and it's always the second one. And then we have the t value, and then p is less than 0.05. And then when interpreting the standardized coefficients, everything stays the same except for the things that I've highlighted here. So in interpreting the regression coefficient, it changes to, for every standard deviation increase in x1, y is expected to increase by, this coefficient will be different, 0.24 standard deviations. So we're now not talking about the units of the variables, but we're talking about in terms of standard deviations. So for every 1 standard deviation increase in x1, y is expected to increase 0.24 standard deviations. Okay. Now we'll move on to the multiple linear regression. And in this example, we have 2 predictors. So I'm going to create a new object called model2. Using the LM function, I'm going to estimate a regression model, which is y predicted from x1 and x2. And again, our data set is the reg data 2 data set. And then for our output, I'll request a summary of model 2. So this first line will run and estimate our model, and then the summary will give us the output. Okay. So again, we have our intercept here, but what we're most interested in are the coefficients. So we have the coefficient for x1, 0.7151, the standard error, the associated t-value, and then the p-value here, which again is less than 0.05, so it's statistically significant. And then we have the coefficient for x2, which is 0.8948, its standard error, the associated t-value, and the p-value, which again is less than 0.05, so statistically significant. We have our R squared, so the addition of x2, we now explain about 14% of the variance of y. And then Adjusted r squared, still pretty close to the r squared, so we're fine. And then on the bottom here, we have the F statistic. So 11.84 on 2 and 147 degrees of freedom. And the p-value is a really small number, which is less than 0.05. So the model is statistically significant. Or another way to think about it is the combination of x1 and x2 provides significant prediction of our criterion y. Okay. And then the last thing that we'll do in R is run the same model, but use the scale function to get our standardized estimates. So again, I'm going to change this to model to scale, and then I'm going to wrap each of the variables in the scale function. Okay, and then just make sure I change this to scale. I'll estimate the model, and then I'll request a summary. And then again, the only thing that we care about here are the coefficients. So here we have 0.2165 because it's e to the negative 1, so we move the decimal place, or we move the decimal one place to the left. And then the same thing for this one. So it's e to the negative 1, so it's moving this decimal point one place to the left. So it's 0.2850 for x2. Everything else stays the same. And so here I have the example write-up for the multiple linear regression examples. So for the first one, a multiple linear regression was conducted to test if x1 and x2 significantly predict y. The results of the analysis suggest that the regression model significantly predicts y. And then here again we have our statistical sentence with our degrees of freedom, our F statistic, and p is less than 0.05. The model accounts for approximately 14% of the variance in y. x1 significantly predicts y. And remember, when we have more than one predictor, we're looking at the prediction of y by x1 over and above the effect of x2, or holding x2 constant. And then we have our statistical sentence here for the t-test of the coefficient. So degrees of freedom, t-statistic, and it's less than 0.05, so it's significant. And then our interpretation of the coefficient. So holding x2 constant, y is expected to increase 0.72 units for every unit increase in x1. And then next we'll do the same for x2. So x2 significantly predicts y over and above the effect of x1. And then here we have our statistical sentence for this coefficient, and then our interpretation of the coefficient. Holding x1 constant, y is expected to increase 0.89 units for every unit increase in x2. Okay. And then again, I've highlighted here the only changes when we're looking at the standardized, the interpretation of these standardized coefficients. So everything stays the same, but now everything is increasing in terms of standard deviations. So holding x2 constant, y is expected to increase 0.22 standard deviations for every standard deviation increase in x1. And similarly for x2, holding x1 constant, y is expected to increase 0.29 standard deviations for every standard deviation increase in x2. So that's the example write-up for the standardized coefficients. All right, so we went over correlations either for two variables or your entire data set. We estimated and interpreted our simple linear regression with one predictor, and we did that for the variables just in their raw scale, and then we did it for standardized variables, and then we went ahead and did that that same thing for a multiple linear regression with two predictors. So with that, that concludes our video today on correlations and simple and multiple linear regression in R.